Hey guys, so today I'll be talking about sequences, series, and sigma notation. So let's go over what sequences are. Just first beginning. Sequences can be defined to be like a set of numbers. Let's say the numbers. Sorry, 1, 2, 3, 4. These are sequence of numbers, or like 6, 5, 4, 3, 2, 1. So these are all sequences of numbers. So it can be any number, to be honest, and like if they have certain special properties within them, they can be divided into certain special sequences, and we'll talk about them later. And sequences can also be finite or infinite, like these ones are finite sequences because these have a particular end in them. But we can also have an infinite sequences, like let's say the sequence of all positive integers. So we show that by 1, 2, 3, and this goes on. We show, and to give a notation to it, we write it like this. And to show the set of all integers, we just do it like this. And this comes up to this. So this is nothing but a notation for a set of integers. Moving on to series, because when we have the terms in the sequence and we take the sum of them, we have a series. So let's say, or let's consider our original sequence 1, 2, 3, 4. So this 1, 2, 3, 4 would be a sequence, but this in turn will be a series, right? And this would be how much do this 1 plus 2 is 3 plus 3 plus 4 3 plus 6 is 10. Yeah, and so that yeah, that's it. Now we'll be going over the sigma notation. So to show this kind of series, also the series can also be finite or infinite. Like this one is a finite series, but we can have another series. Let's say you're told to find the sum of this series. Let's see, like we'll do a question. Let's say there is x, and the sum of x is defined as following. So it's 2 plus a half plus 1/4. Oops, sorry. 2 plus 1 plus a half plus 1/4, and keeps on going. So every term there's a common ratio that's half, and this keeps on going. Let's say you're given to find the value of x as an integer, and we need to find this, and this thing is an infinite series. And we'll look into how we can solve these sort of sums later on, but I can show you how we do this. So we take this, so let's say we multiply this by 2, so it's 2x is, this is 4 plus 2 plus 1 plus a half, and this keeps on going. And let's consider x once again, and here we'll write the terms like this: 2 plus 1 plus half. So since there are infinite number of terms, it doesn't really matter if it's take the difference, and it will be x, this will be 4, and this keeps on being zeros. And here the sum of this entire sequence is 4, so x equals 4. So we'll look into how we can solve this sort of problems later, but yeah, this was an infinite series. This was an infinite series as it was a sum of an infinite number of numbers, and this was a finite one. However, it's very tedious to write this. It's very tedious, right? Very tedious. So to remove this tedious thing, we introduce the sigma notation. The sigma notation. Let's go on to a new page. So what is the sigma notation? So let's say we have to represent another thing. Let's say that we have to show the sum of all positive integers from 1 to 100. sorry, it's 110, 1 to 100. We need to show this somehow. We'll learn how to calculate this later on. If we want to represent this, we can definitely do it in two ways. Let's say the sum is s, and we can write 1 plus 2 plus 3 plus dot dot 100. But a smarter way to do this would be to use the summation sign. So summation sign looks like this, and we use one variable, the iterating variable. Let's say you can take anything. Let's say here we take I is equal to 1, and yeah, let's put this over here. And I from 1 it goes to 100, right? We put the variable here. So what does this mean? So first we have the variable here I. So the first value I takes is 1. So 1. Next is 2. Next is 3. That comes 4. And then this keeps on going till it reaches 100. And this is the same thing as we had here. Let's take some other example, as this was quite simple. Let's say we have to find the summation of I equals 1 to 10 of, sorry, of 2 to the power I minus 1. So how do we show this now? And this is nothing but we take I first is 1, so 2 to the power 1 minus 1, then 2 to the power 2 minus 1, then 2 cube minus 1. This goes on, so we have 2 to the power 10 negative 1, and this is 1, this 2 square is 4, minus 1 is 3, 2 cube is 8, minus 1 is 7, and then this goes on to the power 10 negative 1, which is some number I'm not calculating as of now. So yeah, this is a smart way to show this. So here, what do we do? We have the iteration variable, that's I. We put I. This is a general term of the sequence. This is the general term. So every term in the sequence, or let's say series, because the sum can be represented as this form. And we also have some special of these sort of sigma notation. Let's say we have to indicate the sum of all odd integers. Let's begin with even. That's easier. So let's think about this for a moment. If something is an even integer, what would it be? Okay, even it has to be positive. Let's mention it for simplicity. So if a number is even, or number is even if and only if it is divisible by 2, right? So every number that is even must be divisible by 2. So it must be of the form 2 to the power k. So let's say any even number, let's say 1000. So 1000 can be written as 2 times 500, or 7000. Okay, 50. Let's say take a small example, like 26. It could be written as 2 times 23. So every number over here, any even number can be represented by definition as a product of 2 and another number that we have here. So if we want to make the sum of all even integers, we just give summation. And here we use 2k, and k goes from 1. And now, since the infinite number of even integers, we just give it infinity. So this is nothing but 1 plus, sorry, 2 times 1 is 2, plus 2 times 3 is 4, plus 6 plus 8, and this goes on to infinity. And that's how it works. So just an overview, we went over what sequences are. It's a list of numbers. It can be finite or infinite. Finite ones are these 1, 2, 3, 4, they just end. Infinite ones are ones which don't end, like the set of all integers. And if we take the sum of the numbers in a sequence, we have a series. Like here, and similarly, we have a finite series, like 1, 2, 3, 4, 5, we have 10. We infinite series of these numbers with a common ratio is half, and we will look into it later how we can do these type of problems where there's a common ratio and the series becomes infinite. And then we also looked at what the sigma notation is. This notation is the sigma sigma notation. And yeah, that's what we have gone through. And yeah, That's it for the first thing. Let's go through some more problems of it also. So let's say we have to represent something. Okay, let's say, sorry, yeah. Let's say we have to represent the numbers 5, 10, 15, 20, and this continues in the form of sigma notation, using the general term. So here what do we see? It's 5, it's 10, it's 15. So every number can be represented in the form of 5 times a number k, right? So 5 times 1 is 5, 5 times 2 is 10, 5 times 3 is 15, right? This is the general representation. So the general representation that we have of a number is 5 times k. So we can do this by taking sum of all these numbers and k is equal to 1. And since this is an infinite sequence, we put infinity to it, and this is nothing but 5, it's 10, it's 15, and this keeps on going. Let's take another one. It's quite interesting, like 0, 3, 8, 15. So looking into this, it's messy, it's a bit weird. Yeah, it looks fine now. Looking into this might seem a bit weird initially, because there is no common ratio between these numbers, as the other previous ones where the common ratio was 2. Sorry, where we could add 5 to every number into it. And here, there isn't any common ratio or any common difference between them. But if you look into it more carefully, you can see one pattern emerging. I'll talk about it now. So let's take another pattern and I'll show you how it comes. That's 1, 4, 9, 16. So here, this pattern looks quite familiar, right? Because it's a squares of, sorry, square of first 4 integers. If you correlate both of them, you can see this pattern is just a difference, -1, -1, and this is the same thing, right? So each of these numbers in this pattern can be shown as 1 square subtracted from 1, 2 square subtracted from 1, 3 square subtracted from 1, 4 square subtracted from 1. This goes on infinitely. So if we want to represent this as a form of the sigma notation, we write the summation of, let's say, I is equal to 1 and I squared -1, and we take this to infinity. This is our answer. This is quite simple, and a bit of practice will get you through it. And yeah, that's it for today. I'll meet you the next time.